we've just had a play with our molecular models, and we have made two isomers that have the same structural formula but look different in space. So the way that I like to think of optical isomerism is things that just look different. There's no other way to tell them apart. They have the same structural formula, molecular formula. Actually, they have pretty much the same everything. Boiling points, melting points. But if I make a model of them, they look different. They're called optical isomers, or they're called stereoisomers. This is the other word you'll often see. Good if I can actually spell it right. And the one that we made was butane-2-ol. Alright, so we made butane-2-ol. And we found that CH3, CHOH, CH2, CH3 could, in three-dimensional space, be put together two different ways. Now, this is all well and good if we had molecular models to play with in an exam, or if we had them around us all the time, or if we had some computer program that we were allowed to use in assessments to identify stereoisomers, but we don't. So what we need to be able to do is to identify when a compound has this thing called stereoisomerism and when it doesn't. And what we're looking for is a thing called a chiral carbon or an asymmetric carbon. Chiral is spelled this way, okay? So an chiral or an asymmetric carbon. What that means is it can make 4 bonds, so it's got 4 different groups or atoms bound to it. 4 different groups or atoms bound to it. In your definition, don't just say 4 different groups, don't just say 4 different atoms, because sometimes it is carbon, there are 2 carbon-carbon bonds, but they're different groups. Sometimes it's just different atoms, so it's both. 4 So I'm looking for that one in this compound. So let's start going through them and crossing them off if they're not. If I have a look at the first one, it's got 3 carbon-hydrogen bonds, so that can't be chiral, because 3 of the bonds are carbon-hydrogen, so it can't be this one. I get to the next one. It's got a carbon to a CH3. Notice I'm talking about the whole group there. Carbon to a hydrogen, carbon to an OH, and a carbon to a CH2CH3. They're all different. So this is a chiral carbon. We often show it with a star or an asterisk, just to help us identify it. This will become important in a moment, because on a bit of paper you have to be able to show that they are different in three-dimensional space, which means you have to be able to draw three-dimensional diagrams of these things, which is a little bit tricky. I'll work my way through just to make sure it doesn't have more than one, what we call stereocenter. A stereocenter is what we call the area where it's got optical isomerism. And I say, oh look, 2 hydrogens on that, so it can't. 3 hydrogens on that, so it can't. Okay? So I have got a stereocenter here. So what do I do with that stereocenter? Well, the name sort of implies it's the center of the molecule. I'm going to draw it at the center of the molecule. Every time I do a three-dimensional diagram, I have to show something sticking out of the page and something disappearing into the page. So how do I do that on a bit of paper or on a whiteboard? We've got some conventions in chemistry. So generally what we do is we show one of the groups flat on the page with a line. We show another group at about 109.5 degrees roughly. So you go for that tetrahedral shape. We're not going to measure it. It's about there. Okay? For another one that's sitting flat on the page. Then what we do is we have one that's going directly behind into the board. And we show that with a series of dashed lines getting smaller and smaller down to a point. Then we have another one that sticks out about here. So I show that with a triangle. So it sort of appears to be coming out of the board at me. This is my general shape of my chiral or asymmetric carbon. This is this one. Now, I draw the same thing next to it to show this optical isomerism, but what I do is the mirror image, which means this one here will stick out of the board, This one over here will be flat. All right, so I'm going to draw a complete mirror image of it. And there we go. Now I've built this, I've got the stereo center for the two optical isomers. And they look like mirror images, roughly, don't they? Within the limits of my precision of drawing freehand. Now I need to put some things in there. Whatever I put here has to go in the mirror image spot. Whatever I put here has to go here, and so on. And actually, it doesn't matter which way around I do it. I like to put the hydrogen at the bottom or the top simply because I use it as a point of reference for myself. But there's no right and wrong here. So, let's just work our way through. CH3 is our first one. Let's put it there. I prefer to see it as H3C so I can see the carbon-carbon bond. Not important though. Okay. Then it's just CH, so I've got the H, OH, and CH2, CH3. So I've just worked through that one, then that one, then that one, then that one. The 4 different groups. Okay? I'm just going clockwise. It's arbitrary at this stage because at this level you don't need to be able to name it as, well, there's 2 ways to name these, alright? But you don't need to be able to name them. You'll often see it with organic compounds, but particular ones in biology. There's L amino acids and there's D amino acids. There are L sugars, there are D sugars. Some of them exist in nature, some need to be manufactured. Nature chooses to make one optical isomer of things when there is optical isomerism and doesn't make the other one usually. And the reason for that is that most things in nature are made within enzymes' active sites and they're a certain shape. These take up space differently, so they don't, if they don't fit in the shape or can't be made by that shape of enzyme, they won't be made. So only one of them will be made, not the other. Okay. Right, now, we've built this one arbitrarily. We can't be arbitrary about this one. We have to do the mirror images. Okay? So, OH. Don't have to go to CH3 that way. I'm just sort of exaggerating the point that it's a mirror image. Now, if I was to make molecular models of both of these, they would be non-superimposable mirror images. They would not be able to be superimposed over each other. They'd have a different group in a different place at the bottom. If I got the H and the CH2, CH3 in the right place, these two would not match up. They'd be over it. And OH would match up with CH3. Okay. Why is this important? I've sort of alluded to it. They're actually most important because of their importance in nature, in proteins, in enzymes, in things like glucose, that sort of thing. Glucose is dextrose, so it's a particular optical isomer. That's why these are important. They actually have exactly the same inorganic chemical reactions. They have the same melting points, the same boiling points. Everything is it's the same about them, apart from one physical property. If I was to pass what we call plane polarized light, what that means is I put some light through a polarized lens, so like just sunglasses. If I put light through that and I put a detector at the other side that can pick up that slot of light, what happens when light passes through a solution? Polarized light will be bent a little bit one way. But actually what happens, these two rotate that light opposite ways. So if I had the D isomer, it might rotate the light that way. And if I have the L isomer, it'll rotate it the opposite way. And I can use a polarized detector at the bottom to see, where I need to turn my other polarized lens to allow the light to go straight through. And that's how we can detect if we've got a mixture of isomers or if we've got a pure substance, and it also tells us which isomer we've got if we have only got one of them present. Okay. So, basically the same chemical reactions, same physical properties, except for the rotation, and please call it rotation, not bending or anything like that. The rotation of plane polarized light is opposite. Okay. you need to identify chiral or asymmetric carbons. You need to be able to say that they are a carbon which has got 4 different groups / atoms bound to them, which is why they have the same structural formula, but they occupy space differently. So they are stereoisomers. All right, and butane-2-ol is a great example of this.